Welcome to the Explainer. Today, we're going to break down one of the most powerful ideas in all of programming, object-oriented programming, or, OOP.
Okay, let's kick things off with a feeling I bet every single person who's ever coded knows all too well. You've built something, it works, but then, months later, you have to make one tiny change, and it feels like you're defusing a bomb, right? One wrong move, and the whole thing could just blow up. So where does that fear come from? Well, it all goes back to how we used to write code. And to really get why OOP is such a big deal, we first have to understand the huge problem it was created to solve.
Think way back. In the beginning, programming was super simple, right? Just linear. Your code ran from the top line to the bottom. But if you wanted to do something again, you had to literally copy and paste the code. Then, structured programming came along and gave us awesome tools like loops and if statements. It was a massive improvement, for sure, but a giant problem was still lurking. The bigger your program got, the more of a tangled nightmare it became to manage.
All right, let's make this concrete. Just imagine your app has 20,000 users, and you need to add something simple, like two-factor authentication. In those older styles of coding, you might have to track down and change that login logic in thousands of different spots. It's not just tedious, it's a recipe for disaster. This is the exact kind of nightmare that object-oriented programming was born to fix. So, what exactly is this new way of thinking? Well, it's a total shift in perspective. Instead of seeing your code as this one long, boring list of instructions, you start seeing it as a world full of, objects that all interact with each other. And I mean that literally. In OOP, we're basically creating little digital versions of real-world things. A person? That's an object. A car? That's an object. The phone in your pocket? Definitely an object. Each of these things has its own characteristics and things it can do.
So every single object has two main things going on. First up, you've got its attributes. These are just the facts, the data that describes it, like a car's color or its model or the year it was made. And then you have its methods. These are the actions, the things the object can do, like drive, brake, or honk. All its data and all its behaviors bundled up together in one neat little package.
This next slide has the perfect analogy for this. Just think about our own DNA. It's the master blueprint, right? It defines the general structure and rules for being a human. In programming, we'd call that a class. You and I, we're the objects. We're unique, individual instances, all built from that same master blueprint.
Okay, so in the real world, it's DNA. In programming, we call this blueprint a class. It's the architectural plan, the cookie cutter that we use to create all of our objects. Let's actually see how you'd build one. So how do you actually build one? Well, it's pretty straightforward. You start with the keyword class. Then, inside, you create this really special function called __init. It's the constructor. Just think of it as the factory's setup instructions. It runs automatically every single time you create a new object from this blueprint. It's where you set up all the initial properties. And after that, you just add any other methods for the actions it can perform. Okay, but what's up with that word self you see everywhere? This is so important. It's basically a reference to the specific, individual object that's being created right now. It's what makes sure that the data for one teacher object doesn't get all mixed up with the data for another. It's the key to keeping everything separate and organized. All right, so we've got our teacher blueprint. Our class is defined. Now for the fun part. We can start actually creating teachers from it. We can make 1, 100, 1,000,000, as many unique teacher objects as we need, all from that one single plan. Look at this. We're calling our teacher class twice. First, we make teacher 1, that's Surzia. Then we make teacher 2, that's Kasım. Each one gets its own unique ID and name when it's created. Two totally separate objects, but both built from the exact same blueprint with the same capabilities. And this right here, this is the solution. This is how we defuse that bomb from the beginning. The power is just incredible. If we decide we need to change how all teachers teach something, we don't go hunting through thousands of lines of code. No, you change the teaching method in one place. Just one, inside the teacher class, and instantly every single teacher object gets the update. It is clean, it is efficient, and most importantly, it's safe.
But wait, there's more. Seriously, the real magic of OOP starts when we let these classes interact with each other and build relationships. And the main way we do that is through a concept called inheritance. And yeah, it's pretty much exactly what it sounds like in real life.
Just like you get traits from your parents, in programming, a child class can inherit all the attributes and methods from a parent class. It's all about that is-a relationship. Let's look at an example. It makes it super clear. We can have a general employee class, and all it does is store a name. Then we can create a more specific class, a developer, that inherits from employee. A developer is an employee, right? So it just inherits the name attribute from the employee class for free. And on top of that, we can give it its own unique abilities, like a method to code. And I'm telling you, this is a total game changer. For starters, you reuse code like crazy. No more copy and pasting. You write it once in the parent. It also lets you build these really clear, logical structures that mirror the real world. And it makes maintaining your code so much easier because any change you make in the parent class automatically trickles down to all the children. So at the end of the day, you gotta see that OOP isn't just about syntax or rules. It's a whole new way of thinking about problems. It gives us the tools to model incredibly complex, real-world systems, everything from a university's management system to a massive e-commerce site, in a way that's organized, reusable, and can grow over time. It's all about turning chaos into clarity. So the real question is, what real-world system will you model first?